Right, welcome back to this next webinar kind of thing. Today we're talking about ionization energies. Let's see if I can write that down here. Again, I've got the handwriting of somebody very young, I think. I'm still getting used to using a graphics tablet myself. Right. So up to now, we've been talking about the structure of the atom. We've been discussing the nucleus and the fact that the nucleus contains protons and neutrons and it's surrounded by electrons. So if you remember just a brief thing, you've got the protons and neutrons. Let's just quickly do something for helium. There we go. Oh, that's dreadful. As I say, I'm trying to find the best tool to use for this. I don't want to use PowerPoint slides because I think one after the other they get boring. But anyway, so that's it. So we've got your protons and neutrons in here. I'm not going to go over this because you've already seen it in the last couple and you're going to get bored. I mean, you've already done this at GCSE, so there's no point in patronizing you any further. But if you bear with me, what we're talking about now is the removal of electrons. Now, the first thing you need to understand with these is electrons are obviously orbiting the nucleus of the atom, and they all contain packets of energy. So each one will contain a certain amount will need a certain amount of energy to remove it out of the orbital. So to kick this out of the orbital into the next orbital or have it fly off, you're going to need to put a certain amount of energy into the material for that to happen. So that is a lot of what ionization energies are all about. And obviously the closer the electrons are to the nucleus, the more energy that will be required. Oh, this is just terrible crumbs. Oh dear. It's a work in progress. I'm not really used to delivering with these things, but now I can't. There we go. Right. So to make matters even more complicated, I may as well tell you is I've gone to a dual monitor setup, and I don't know. I think it's recording from here as opposed to. I'm just going to have to run with that one for now. So if you can imagine that weird one's the first orbital, then you've got one on the outside, and then one on the outside. Yeah, if we just go to 3 for now, that is really dreadful. But if you can imagine these are a bit more circular, it's going to take more energy to remove the electrons in here than from here and from here. And that's simply because these are closer to the nucleus of the atom. And as you go further and further away, it should take less and less energy to remove the electrons. That's basically what ionization energies are all about. How do we know about ionization energies? I might as well just skip that, move down to the next slide. Maybe can I do that? There we go. So let's just move down to the next slide. So we know about ionization energies, we believe, from something called mass spectroscopy. And even though that is something you will meet, let's see if I can write that. Spectroscopy. So essentially, what we're talking about here is you get your sample and it's a gas, right? It's a gas. And what we're doing with this is we're bombarding it with the beam, okay? And we're bombarding it with a beam of electrons. This is, sorry, bombarding it with a beam of electrons. This is why scientists use symbols. Yes, there we go. And what we end up with is positive ions. So now, so this is the whole sort of concept of mass spectroscopy. So you're bombarding a gaseous sample with electrons, and you're knocking the electrons out of the orbitals of the gaseous elements inside there. So to knock out the first ones would require less energy, and then as you go further and further and further down into the orbitals closer to the nucleus, it's going to require more energy. So to give you an idea of that, let's pick on something called sodium. Now, sodium, as we all know, is the chemical symbol of Na. So when you've got Na, gas, and you go to Na plus gas plus an electron, we've essentially ionized it. And off the back of that, I can tell you that to take that lowly single electron away that sodium has, and sodium's quite pleased to give it to you, by the way, it takes plus 496 kilojoules. I'm saying kilograms there. Dear. I'm using a pen here. There we go. Right. So I wanted to remove that because we've got to get the units right. All right, kilojoules per mole. Okay. So essentially, that is the first ionization energy of sodium, 496 kilojoules per mole. So what does that mean then? Right. If we start off with 1 mole of sodium atoms and we turn it into a gas, the amount of energy required to remove an electron from every single atom of sodium in a mole of gas is going to be that amount. That is the definition of what of the first ionization energy is. It's the amount of energy needed to remove 1 mole of electrons from 1 mole of atoms. Okay, that is what the first ionization energy is. I'm going to have to, I won't even try writing that down here somewhere, but by all means, feel free to pause this and make a note of that for yourself. So let's move on then. So if that's going to be the first ionization there for sodium to remove 1 electron, what is it going to be to remove, oops, daisy. Oh dear, oh dear, oh dear. I'm not too good at the moment. First thing in the morning. There we go. Let's just stick with that. So, right, gonna have to better this. So sodium plus then in gaseous state. Now remember when you're writing these formulae, the state symbol should always be there. Okay, you get a mark for that in the exam. So we're going to go from Na plus now across to Na2 plus, which is also a gas. And that's a gas there that looks like a solid, but it is actually a gas. Okay, plus an electron. Okay, and that is going to require the energy of plus 4563 kilojoules per mole. Okay, so straight away, this is the first ionization energy. This is the second ionization energy. All right. So what we've done now is that's to remove the electron, and we'll see what we're talking about here because I'll put the diagram up for this in general. Let me now nip down and put down the third that we've got. So now we're going to nick an electron from Na2 plus. So sodium is already lost 2 electrons, and we're going to go to Na3 plus. Now that isn't going to be a state that sodium is going to like, okay? That isn't going to be a state that sodium enjoys. It does not like being there. It's happy with the top one, but if you notice the massive amount of energy to remove it suddenly has gone massively up, okay? In fact, to take a second one is going to be the equivalent of, and wait for this, what do you think it's going to be? 6,913 kilojoules per mole. Yeah? And that is the third ionization energy. Okay, hope you're okay with my shorthand here. So what you've got here is you've taken the first electron out of sodium's outer orbital, and that's quite straightforward because sodium, to get to a more stable state, needs to lose that electron. So it's happy to lose that, not a problem. It doesn't take an awful lot to lose that. But if you want to take the next one out of its stable energy level, we'll talk about that shortly. That's going to be a massive, massive, massive amount. Look, it's almost 10 times the energy to remove the second electron. And then it's a little bit more to remove the third one. So what that's telling us is, it's telling us about the electronic orbitals of sodium. It's hinting at the existence of those. And if you remember when we said that the first ionization energy is the amount of energy required to remove the first electron, yeah, from 1 mole of gaseous atoms, okay, that's what the first ionization energy is. So here what we're saying is, it's taken that amount of energy to remove 1 electron from 1 mole of sodium atoms, okay, and then it's taken that amount of energy to remove the second electron from 1 mole of sodium atoms. That's how we must think of this. And also notice something else, they're all pluses, yeah, the plus. So it's taken plus 496 kilojoules per mole to remove the first electron, plus 4,563 kilojoules per mole, blah, de, blah, de, blah, de, blah, plus, 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 plus. That tells us we are having to put energy into the system to remove those electrons, okay? If it was minus, that would be the amount of energy that's generated. It's an exothermic reaction. This is endothermic, E-N-D-N. Thermic. I love creating a rod here, don't I? Thermic. Okay. Endothermic. Really must try to improve my handwriting. Yeah? So it's an endothermic reaction. So it's energy going in. So what we can see here is steadily going up from sodium plus, which is the sort of lower energy state that we're trying to remove it from. Not the lower orbital, I hasten to add, but a lower energy state. So it's going to be easier to remove electrons from that, but progressively harder as you get further down. So what's happening here essentially is you're getting down further towards the nucleus of the of sodium. And when you understand that sodium has got an atomic number of 11, so that's the number of electrons that sodium has got moving forward. So what does that mean exactly, moving forward then? I mean, how does that fit in? Well, I'm just referring to my notes now as I speak to you. So now we've discussed that, let me really try creating a rod for my own back here. Let's draw the ionization levels chart for sodium then, roughly. So let's put in our y-axis here, and let's put in our x-axis across here. Now we're talking, as we said, that we have got 11 electrons to play with. So if this is the energy here, okay, and if we talk about here the electrons, number of electrons, okay. Now, obviously, if you think about it, the energy is increasing up this way. So if we talk about the first one down there, that one is the furthest away from the nucleus of the sodium atom. So not a lot of energy. Okay, this is our 496 kilojoules thingy that we discussed earlier on. Now, if we then take a jump, yeah, that's the second one we moved there. And then suddenly, out of the blue, if I sort of reverse engineer this a little bit, we go up there. So 1, 2, 3, 4, 5, 6, 7, and then 8. So here we go. So the energies required are not all that great after that, stepping up and up and up. Still takes more energy, but these are the next 8 electrons. Yeah, so 9, 8, so 10 and 11. So then to get up to the next ones, you've then got a bigger jump to take these up here. And what this tells us is that sodium has an electronic structure. This hints that we have an electronic structure. So down there, if you look at this, is where you got your 496 kilojoules per mole sitting here. Okay, I'm not going to scribble that one out, but here you got your 6913, and then it's going to get progressively higher and higher and higher. So if you can imagine how it's jumped from 4563, you can only hazard a guess as to what you're talking about here, because when you get into these electrons here, you're pretty much talking about the nucleus of sodium. So as you can imagine, if that's the sodium nucleus there with 11 neutrons packed into the thing, and you've got literally like Mercury orbiting around the sun, quite a lot of gravitational pull. I shouldn't really use that terminology when talking about atoms. So about that, let me just get rid of this. This is just my email open up as well. But if you look at this, the amount of energy that's going to be required to pull those two is going to be phenomenal. So that's a lot of what we're talking about here in terms of the ionization energies. So you can see here that as you're getting closer, see this is where you're closer to the nucleus down here, and as you go furthest away from the nucleus down here, furthest away down here, and as you go further up and up and up and up and up and up, you're getting closer to it up here. And that's why the ionization energies increase. We know this because as we increase that electron beam to remove another electron, remove another electron, and remove another electron, you can see the energies. It's getting harder. So if you think of it this way, the more energy you're going to have to put in, the harder it is to take that electron. Sodium isn't happy to remove it. I mean, where sodium's happy really is in this state here. Yeah, you will come across the stable octet in chemistry quite often. This is to what it's referring to. It wants this outermost set of electrons full. Yeah, it wants this full. This is the outermost orbital, and it's only got one electron there. So it's going to be far easier for sodium to lose that than to fill it. And you'll see the adverse of that, or the inverse of that, when we start talking about noble gases. So a lot of this, and I hope you kind of understand it, talks about the ionization energies and why they increase. And again, I hope I've put this to you in a way that you understand. Yeah. So what I'm going to do is leave it there, and then when we come back next, we're going to be talking about the atomic orbitals of elements and how that relates to what we call the shells, the atomic shells around the nucleus of an atom, and see how that marries up then to electronic configurations. So that's where we're heading to next with this. So I'm going to call a stop there, and that's where we're going to go to next. Okay, I think after 18 minutes, give you a chance to digest that now. Thank you for watching.